All right, so let us begin today's meeting. It's a great pleasure to be here. Thank you very much to the organizers for giving me this opportunity. My name is Denis Fedoseev. I'm originally from Moscow State University, and for the last 7 years I've been doing some research in geometry, topology, and all those geometric things. And for the last 2 years I began to apply those geometric ideas and geometric constructions to machine learning and data analysis. So during some joint project program of the university and the Huawei Corporation, we tried to use geometric methods to make machine learning algorithms better, to better, find anomalies in images, to improve face recognition and stuff like that. And today I'd like to share some of these ideas, some of the basic constructions and their applications. So how geometry can actually help in data analysis and enhance our methods and algorithms. So the overview of my talk is not very long. So first I'll be speaking about what is a manifold. So this very basic construction, very basic object of differential geometry. Then we'll look into how manifolds appear in data analysis, why they're interesting, why they're important. And then we try to apply them and study them in two ways. First, we'll discuss the dimension estimation of those manifolds, and then we'll talk about metrics on those manifolds, and we understand why metrics on manifolds may improve the machine learning results, and sometimes they're absolutely necessary. So if we don't look at the manifold, we just can't get accurate results. So let's begin with the most basic thing. What is a manifold? I'll try not to use some very rigoristic approach with a lot of definitions and a lot of special terms. So just if I try to show it, if I try to explain it, then in a very basic sense, a manifold is just a reasonable formalization and generalization, of course, of the idea of a surface. So everyone knows what a surface is. The most common surface we know is just a plane, or if we look for higher dimensions, it could be multidimensional Euclidean space. So like R3 or like R5 or whatever. Manifold somehow expands this notion, generalizes it. So here I have this pretty nice, in my opinion, picture of a torus, another very simple yet much more interesting object, much more interesting manifold. And looking at it, we understand, we see that clearly this torus is not a plane. It's something different. But how they're connected? What is exactly the difference? So, for example, can we take the torus and deform it somehow to get, well, maybe not a plane, but a sphere? Actually, that's a very basic question of differential geometry and more specifically of topology. So if I have two surfaces, two objects like that, can I, deforming one, obtain another? The answer to this particular question is negative. No. No deformation of a torus is a sphere. But why? I'm not sure that we'll be able to answer this question exactly today, but at least we'll understand the objects we're working with. So how do we construct a manifold? How to, as one talk at some conference was titled, How to Fold a Manifold. So what are the basic constructing blocks of it? So let's take a disk, a usual disk in Euclidean space Rn. For this particular example, I'm taking a two-dimensional disk on a two-dimensional plane. Here it is. Actually, this n, this dimension of the Euclidean space Rn, from which we take the disk, later will become the dimension of this manifold, of this whole manifold. But for now, we work with a very simple object, maybe the simplest possible, with an open disk. And then we start to deform it. In this example, I took the disk and started to deform it in three-dimensional space R3. Actually, I can take some high-dimensional space in for example, deform it in R4, R5, or whatever. And later we'll see that in reality, this ambient space where we do deform the disk doesn't matter. It may not exist at all. But for now, for our example, let's take this particular case where we deform our two-dimensional disk in a three-dimensional space. One thing to note is that this initial disk doesn't have to be circular. So here I drew a circular disk, but actually I don't need it. Any disk at all is suitable. So what I mean on saying any disk, it means that any object, two-dimensional, which can be continuously deformed. When I say continuously, I mean that I'm not allowed to glue some points together or tear my disk. So, for example, I can describe it like that. Any object on the plane, which by continuous deformation
disk in n-dimensional Euclidean space ball.
Ball, yes. For
disk if n equal to
well, it's a question of terminology. Usually, in my area, in my differential geometry, n-dimensional balls are also called n-dimensional disks. It's just synonyms. And in that sense, yes, the circular disk is a two-dimensional ball. So we take anything which could be continuously deformed into like this circular ball or disk, however we want to call it. And then we take our first deformed disk, take the second one, and glue them together with some overlapping. So here I have this picture. It's not exactly what I mean, since here you can see that we have two disks, the blue one and the green one, but they are glued by their boundary. They are not intersecting. Actually, imagine that those blue and green disks actually have some overlapping, so they are just like lying one on another, and because of this coloring, we can see it. And so we continue this process. We are taking more and more disks of the same dimensions. That's important. So in our case, we'll take all the disks of dimension 2 and continue to construct this patchwork-like surface. What we end up with is a manifold. So speaking more precisely, what is a manifold? It's some set of points in, for example, R3 or Rn, such that the neighborhood of every point, small enough neighborhood, looks like a deformed disk from Rn. So in our example, any point, if we take, let me think, yeah, if we take any point here and take a small neighborhood of it, it will look like just a deformed disk from R2. That's the idea of a manifold. So we begin with a simple thing, a part of the Euclidean space, for example, a plane, and then we make something more complex, more interesting out of these basic pieces. One more step of abstraction, which is actually quite important in many areas, maybe not so much in data analysis, but still. We consider this manifold not to be living in some ambient space Rn. So like here, we had our torus glued from these pieces to be lying in the R3. But we can forget about this R3. So we can look at this manifold like it is existing all by itself. There is no ambient space where it lies, or how the geometrists say the space the manifold is embedded into. It's just all the world we live in. So we have only this manifold and nothing else. At first, this notion, this idea of the surface being all the points we can work with could be a bit, I don't know, distracting and unclear. But there is a very real-life example which somehow, for me, illustrates this idea very, very well. Here it is. So that's a picture. I took it from Wikipedia. It's credited to NASA. And it's an illustration of the current incarnation, I'd say, of the Big Bang theory of how our universe appeared and developed. And so for me, when I first heard of it. It was very, very strange. How can I imagine the Big Bang? So the point in time before which our universe didn't exist at all. So how our universe cannot exist somehow. For me it's strange. I don't know, maybe for you it's more, I don't know, understandable, but for my imagination it was hard to fathom. But then I looked at this picture and I think I understood it better. Look, this thing here is our space-time. So that is the, let's for the sake of simplicity say, four-dimensional manifold where we live. So 3 dimensions of space and 1 dimension of time. It's all one surface, one manifold. Complex, big, convoluted, I don't know, but one manifold. And that is the example of the manifold all by itself. There is no ambient space where it lies in. It's all, literally, all our universe. So there is no ambient space to lie in. All the points we have, every moment in time, every point in space, lies on this manifold. And then we can see that the Big Bang is just one point on this manifold. It's just here. So it's not that before this point there was no universe or whatever. It's just that when we try to look at our universe from this linear time point of view, when we're moving like from here to here, then yes, in that sense, there was nothing before, just because it's the local minimum of this surface. So if you can see, this is the local minimum in this direction. But if we look at this manifold in general, look at it, and we see that, well, it's just one point on the manifold. And yes, that is a topological manifold in the sense that it doesn't lie in some ambient space, in some higher dimensional universe, I don't know. Well, maybe it does, maybe it doesn't. According to current theories, it doesn't. But from our geometric point of view, that's a manifold we live in. And that is, it's, well, kind of beginning, but actually it's just one singled out point on the manifold. So now we have some better understanding of what a manifold is. So again, some set of points such that a neighborhood of every point, local neighborhood, looks just like the formed disk from Rn of some fixed n. So this n is constant for all the points of the manifold. And let us move to the second, or more maybe applied part of this idea, how to find manifolds in data analysis. Why are they interesting? And first of all, we understand perfectly that geometric representation of data points, naturally and frequently appears in both statistics, in data analysis, in machine learning, and whatever. So here I have 3 examples which I like. The difficulty is different. So first one is just a linear regression, where we so put every data point on this 2-dimensional plane and then find the line which in the best way approximates them. Then here we have the principal component analysis diagram, where again we have a lot of data points scattered somehow in the 2-dimensional plane, and then we try to get some, in reality, geometric characteristics of this set. So even though principal component analysis is sometimes formulated in statistical terms, so we take the covariance matrix, we take some eigenvectors, sort them, and take the longest ones, but actually we find these vectors which are spanning, in a way, our cloud of points. And then we forget about the shortest ones and project our cloud of points on the lower dimensional subspace, making our job easier, because fewer dimensions, and it is the easier it is to work with the cloud. And the last but not least example here is, it's a diagram of convolutional neural network, or at least the first part, the convolutional part of it, when we begin with an image, so this robot here, and then we start to contracted with some kernels many times in many layers. And in the end, we have the output, and this output is just a long, long vector. So it is a point in some abysmally high-dimensional feature space. So again, we transitioned from the image, in this case, to some point in some high-dimensional space, Euclidean space. And as you probably know, the dimensions of such spaces are tremendous. So for example, in the concrete examples I worked with, we had like 1,700 the dimensionality of this space, and that's a lot. That's really a lot, and it's quite difficult to work with such spaces, like just taking them raw for what they are. So, okay, we have geometric representation, but where are the manifolds? Of course, Euclidean space, Euclidean plane here, here, and Euclidean space here, all of them are manifolds, of course, but they're not very interesting manifolds, and there is no real reason to introduce this whole manifold theory to just describe Euclidean spaces. But actually, what is important for us is the so-called manifold hypothesis. That's what it is called in the literature. For example, here is one of the more on the point papers on this matter, so testing the manifold hypothesis. And what this hypothesis states, that actually, if I take cloud of data points in some high-dimensional feature space, and I take those points not arbitrarily, so I don't just take some probability distribution and shoot those points into the space, but I obtain those points from some real-life data. So, for example, if I take this image and then, using the neural network, transform it into the long vector in the feature space. In that case, those points, they don't occur in this Euclidean space randomly all over the place, but they actually lie along some quite low-dimensional manifold or manifolds inside that high-dimensional space. Of course, when I say here they lie along, I don't mean that they exactly lie on the surface, so that there is some torus, two-dimensional torus in a 1,700 dimensional feature space, and all the points are situated exactly on this torus. No, that's not true, and that couldn't be true. Well, maybe it could, but in that case our world would be much different from what it is. But they lie in a close vicinity, so in a small neighborhood of this low-dimensional manifold. And for the purposes of our research, we can actually consider them lying on this manifold. And that means that when we look at the cloud of points, of this data cloud, we actually can and should try to find this manifold structure, so the manifold where those points actually live, and apply the knowledge of this manifold to better understand the structure of this data. And there are two maybe major directions in this study. So first part, we need to understand what is this dimension. So how large actually is this manifold? In some sense, what is the volume of the space of the place, better to say, where those points actually live? So, for example, if I take, I don't know, this linear regression, and imagine then all these points lie very, very close to this red line. So here they are reasonably scattered, but imagine that they are very, very close. Then the dimension, actually that is one of the examples of this manifold hypothesis. So then the dimension of the place where these points live would be very close to 1, because this line is one-dimensional manifold, it's a curve. And in all the two-dimensional space, the points would only span something one-dimensional or very close to it. So in general, if we have this 1,700 dimensional space and we have points there, what is the actual dimension? What is the place where we're living in? For example, I can right now give some numbers. So when we were working with some open data sets of images of people, of the faces, photos, we had this 1700 dimensional space, but the actual manifold where those points live was like about 30. So the dimension reduction is tremendous. From more than 1,500, we came to 30-dimensional manifold. It's much easier to work with, to understand, to fathom. And the second part, the second main direction is construction of metric. So this way to measure distances and differences in this sense between points on this manifold as opposed to metrics in the ambient space. I'll talk about that a bit later in more detail, but for now let's talk about one particular method of dimensional estimation. Before I delve into this Minkowski dimension notion, and here we'll have some formulas, hopefully not much. Yes, sure.
Is any joint density function is a manifold? It is a surface, yes?
Yes,
For example,
that is true. That is true. Yeah, sure, sure.
Two argument function.
Absolutely.
Dimension of space, we know from calculus that it is a surface.
Yes, that's right.
Manifold, since the corresponding matrix induced from like a corresponding Euclidean space.
That's right. So one, absolutely. So one of the most well-studied, maybe, and most common kinds of manifolds are just actually graphics of some functions. So, for example, if I have like a function of n arguments, yeah, and then, for example, it's mapping from this Rn into R, then the graphic of it would be a surface, a manifold, in Rn plus 1. And yes, that is an example of manifolds, and of course, there the most common metric is just induced from the Euclidean space. But there are other kinds of manifolds. For example, the ones which can't be, the whole manifold can't be constructed as a graphic of some function, of any function. Such manifolds exist. And in that case, well, there we have to study them with different instruments. For example, we can take them locally, so patch by patch. And again, as I said, not every manifold is considered to be lying in some ambient space, and in that case, I can't induce a metric. I don't have a metric in the ambient space. All right, so before delving into the Minkowski dimension notion, I'd like to say that one of the, again, most common ways to estimate in reality exactly the dimension of this manifold from the manifold hypothesis is this principal component analysis model method which I mentioned. And yes, how it works. So for example, if this cloud is very, very thin again, then I have two principal vectors. One is very short and I disregard it, and I estimate the dimension of the manifold where these points live to be roughly 1. So it's very, very thin area. Of course, it's not exactly 1, it's really two-dimensional, but I can approximate it like that. The problem with principal component analysis is that it usually, in most cases, it overestimates the dimension. So, for example, imagine that my manifold, my data set, is very, very curved. It rounds on itself. And then, for example, it can live on some two-dimensional surface. I'll show you an example in a second. But if we apply the principal component analysis, all the principal vectors would be quite large, and this method would estimate the dimension as the dimension of the all ambient Euclidean space, for example, 3. So sometimes we need some more subtle instruments to look at it. And so here is one of such instruments. For more detail, you can refer to our paper. Well, it's actually a preprint in archive, which were wrote during this joint project with Huawei. So there we used two actually methods of dimensional estimation. One was purely geometric, that's the Minkowski dimension, and the second one was more probabilistic. I won't be talking about it today because our time is limited, but we'll concentrate on the Minkowski dimension. So originally, the Minkowski dimension was devised, and it appeared when people tried to invent what is the dimension of some fractal set. So you know fractals, those sets which somehow repeat itself. So if I zoom in on this set, I'll see the very same set again. And those are not manifolds, they're pretty badly constructed. I don't know how to put it better. And for example, they can have fractional dimensions. And the usual notion of dimension is just can't be applied to it. And so the Minkowski dimension appeared. So let us describe it and define it. So first of all, let M be some set in Rm, not necessarily a manifold, some set of points. And let us cover, I'm sorry for the typo, let us cover this Rm by distinct d-dimensional cubes with side, another typo, I'm sorry, side R. And denote this set by Br. So we usually these d and m are the same. So again, for the sake of simplicity, let us cover the Rm with m-dimensional cubes. And naturally, those cubes are divided into two groups. Some of them intersect our set M, and some don't. So let us consider the number, and denoted by n of R. It's the number of cubes such that their intersection with our set M is not empty. We can understand and imagine then when we make the size of the cubes smaller, this set of cubes intersecting M would better and better approximate the M itself. And the Minkowski dimension is defined as follows. Let us take this number of cubes intersecting M and take it, let's say, in logarithmic scale, so log of this. And here I don't have the basis of the logarithm. Consider it to be whatever, some fixed number. For example, it could be a natural logarithm. Then we divide it by the logarithm of, with the same base, of 1 over R. And we look at what happens to this fraction when we make our cube smaller and smaller and smaller, so when R goes to 0. If this limit exists, of course it's not always the case, but if it exists, then this number is called the Minkowski dimension of the set M. Important thing is that if M is actually a manifold, a real manifold as I described, then this Minkowski dimension exactly coincides with the usual notion of dimension. So with the dimension of these disks, the manifold was glued from. Okay, but how to calculate it, how to get it from our data? Here is the illustration. So here, if we have the manifold, n-dimensional manifold actually, then when R goes to 0, when it's very small, then the number of those intersecting cubes is almost like the volume, n-dimensional volume of this manifold. For example, what is n-dimensional volume? For example, for a curve, it would be its length. For a two-dimensional surface, it would be its surface, its square. Yeah? For three-dimensional manifold, it would be its volume, and so on and so forth. And we divide it by R to the nth power, where n is exactly the dimension of this manifold. From this, we can see that logarithm of n for small r's is just logarithm of v, and v is some unknown to us, but it doesn't matter. It's just a constant. We have some manifold of unknown dimension, and it has some particular volume. So it's some constant minus n logarithm of r. I just obtain it by applying logarithm to both sides of this asymptotic equality. So we can see that logarithm of n is a linear function whose argument is logarithm of r, and the coefficient is exactly the dimension. So if I calculate this n for some r, then for small r, and so on and so forth, then the graphic would be something like that. We would have this linear function, this one. Here we have minus logarithm of r, here it is. Here we have logarithm of n, which we can actually compute. And the angular coefficient, alpha, its tangent would be exactly the dimension we are looking at. So if we have a manifold, that's what we can do. We can break our space into cubes. Then for many values of r, we calculate the n, look at the graphic, calculate its derivative and its dimension. Of course, when we are talking about not a real manifold but a cloud of points, we have some queries. For example, imagine that the r, the size of the cube, is very, very small. It's smaller than the minimal distance between our points, well, somehow normalized, doesn't matter. Then every cube would either contain exactly 1 point of our set or 0 points. Just because if the cube is very small, smaller than this number, its side is smaller than this number, then no 2 points of this cloud could appear in the same cube. And that means that when r is smaller than that, so when minus logarithms is bigger, here it is, we would have just constant. Our function would be constant. It ceases to change. So in that case, we have to carefully find this piece of the curve, which is actually meaningful linear part right here. So before this critical value of logarithm of r, and calculate the derivatives there. Because of that, we can't calculate the dimension exactly, but we can get some estimations. And exactly in this way, in our paper, which I mentioned, we obtained the estimation of the dimension of this point of cloud of points obtained from the photos of people. So this is one of the possible and interesting and computationally quite nice, it's not very computationally hard, ways to estimate the dimension of this manifold.
What is the manifold in the first figure?
Here? Oh, I'm sorry.
Set of points is finite, but
what
is the manifold?
We have this curve, it's dashed. See it here, this curve. And the points lie in a close vicinity of this curve. So the manifold is a curve. It's one-dimensional manifold. In this picture, we had exactly this curve. And we got a very nice straight line, and the derivative is just the dimension 1. In this case, we have just the cloud of points which lie closely in a small neighborhood of this curve. Because of that, again, we calculate the same logarithm of n, plotted as a function of minus logarithm of r. So r is just here, it is the side of the square. So our cubes here are squares. And look at the graphic, and again take the linear part, calculate the derivative, and get the dimension. Yeah.
So you have an assumption that the points are uniformly sampled from manifold?
No, not necessarily.
If they're dense in one side and then they're pretty sparse on the other side.
That is true. That is true. That could affect it. But if we take, for example, if we have a lot of points here, for example, along this part of the curve, and here we have virtually no points, then this method what would it calculate? It would calculate the dimension of this part of the curve, right? But the manifold, it's like the dimension of its every part, neighborhood of every point, is the same. So if I can just calculate the dimension right here, then I know the dimension of all the manifold because it's constant. So in that sense, the Minkowski dimension is pretty robust. So it works pretty well with different sparsity and condensation of data. Of course, some extreme cases could screw the results. I think that there is no absolutely accurate way to estimate the dimension without any misgivings, but it's pretty nice.
But what is the limit log v divided by log r?
This one. This one. Or where? Sorry. So we have this graphic is on the x-axis we have minus logarithm of the side of the square or the side of the cube in general, and here we plot the logarithm of the number of cubes intersecting our set. That's it.
The corresponding manifold is minimal, which depends this or any manifold which.
No, the minimal, actually the manifold which, let me explain. So again, we have this asymptotic equality. So the number of points, the number of cubes intersecting the manifold looks like the volume of exactly this manifold divided by r to the dimension of this manifold. And so when we calculate it for the cloud of points, it would give us the best estimate which manifold those points could lie on or very close to, such that this asymptotic equality holds. That's it. So of course, again, it could overestimate and underestimate the dimension sometimes. For example, imagine that my manifold is something like that. It's a serpent which very densely covers this square. Then most likely, unfortunately, when we have the random points around this serpent, then unfortunately the Minkowski dimension most likely still would see the whole square, and its answer would be 2. So it overestimates. In some cases, for example, if our data is not uniform, then, for example, I could have a two-dimensional manifold, but for some reason my points appear on some line on this two-dimensional manifold. Because, for example, I don't have sufficient data. Then the Minkowski dimension would estimate it, the dimension as 1, but actually it's 2, I just can't see it.
So do you have a theorem that puts these enemy conditions together? At least these days we can recover back.
Right now, I don't think that I have on my fingertips the exact formulation of the theorem, so which conditions should be satisfied for the dimension to be exactly what it is proposed. We have some experimental data on artificial and real data sets, and we see that, yes, the estimation is good. All right, so let me talk a little bit now about the distance between data points, about the dissimilarity. So one of the most, thing that I have not much time left, so one of the most common ways to, for example, work with face recognition, so after the neural network I have these points in high dimensional space, and I try to take in the test point, for example, using the simplest model, the k nearest neighbors model. I just try to understand whether it's one person or another by looking at the closest point to this one. But there are some interesting things which can occur. For example, look here. Those 3 points, green, red, and blue, they all lie in a plane which is parallel to this one. And so, looking at them, we can clearly see that, well, the red point is closer to the green one than the blue one. So this distance is greater than this one. It's, well, just looking at it using, for example, Euclidean distance, or actually any standard metric, any standard distance in the Euclidean space, like Minkowski distance, Manhattan distance, Euclidean distance, whatever. We see that, yeah, those 2 points are closer to each other. And so using the, for example, one nearest neighbor model, we would classify the red point in the same class as the green one, and the blue one in some different class. But what happens when we look at actually the manifold where those points live? Here it is. And we understand that in reality we should have been measuring the distance not in the ambient space, because ambient space knows pretty much nothing about these points in reality. The manifold knows more. And we have to calculate the distance along the manifold. And then between the green and the red points, we see this long way, long curve. And between the red and blue, the curve would be shorter. And we understand that actually our original idea was wrong. When we calculated the distance in the Euclidean space, we got some results, but when we look at the data closer, and when we take into account the manifold it lives on, we see that no, the distances were wrong. And actually this, so red and blue points, for example, should belong to one class and the green to another. Here I have this maybe cryptic paragraph about what a Riemannian metric is. So I'm not sure that I have enough time to delve deeper into this idea, just saying very shortly that usually metric is some mapping between from pairs of points to real numbers, which satisfy some axiom. So the distance is always non-negative. If points coincide, the distance is 0, and we have this triangle inequality. In differential geometry, we work with something a bit different. It's called the Riemannian metric. And in reality, it's just the scalar or dot product into the tangent space to the manifold. So if I take a point, I can consider the tangent space, in the usual sense, the tangent space to the surface. Then I have vectors in this space, and the Riemannian metric just tells me how to multiply them. Surprisingly, this very small, as it seems, information is enough to calculate lengths of curves and so the distance between points. So how do I calculate the distance between two points? I just take all the curves connecting those points, calculate their lengths, and take the shortest one. So hence from the Riemannian metric, I get the distance between points. And, well, so as we can see, the real problem and the real advantage of differential geometry in this setting would be to measure distances between data points, not using the ambient distance, whatever it is, but using the inner metric, using the structure of this manifold where the data points live. So, why knowing the dimension is important? First of all, if the case is pretty simple, like when the PSA is good, is applicable, then we can just straightforwardly reduce the dimensionality of our data set by projecting it to some lower dimension linear subspace. That's what principal component by PSA, I don't know, PCA, of course, component analysis, sorry. What does the PCA do? It just finds this good linear subspace and projects the points onto it. As I said, in this case, it's a very commonly used data set manifold called Swiss roll. The PCA most likely would overestimate the dimension because it's very non-linear. It's very curved. Then the second advantage of knowing the dimension is that, well, I know that there is some manifold, but I don't know what it is and how to find it. And if I have the dimension, then at least I know at what number of parameters, of actual parameters, of substantial parameters to look for. Then the third thing is that I said that Riemannian metric lives in the tangent space, and it appears that constructing tangent space from these just data points we have, this finite data cloud, would be all by itself very good for constructing better distances, better metrics. And this construction of tangent space needs, for example, let me put it like that. If I have a data point and I want to construct a tangent space to my manifold at that point, then I need exactly the dimension of the manifold other points in the neighborhood. It turns out that those points, well, first of all, I only need, for example, 30, not 1,700, but just 30. It's much easier to obtain. And then those points could be obtained artificially. For example, if we're talking about image recognition, we can use the augmentation technique when we slightly distort our image, for example, rotate it or shift it, and those artificially obtained data points would still lie on our manifold in a close vicinity of the point we begin with, and then we can construct the tangent space, and the distance would be much, much better, and the results of image recognition would be, again, much better. We had such experiments. And final bullet in this slide is algorithms for geodesic shooting. So geodesic is exactly this shortest curve, and if I take a point, I can take some direction, and knowing the dimension, I can construct the geodesic which lies on my manifold and goes, well, wherever it goes. For example, if I, in this way, construct geodesic which connects one of my points to another one, then here I have the nice inner distance between those points along the manifold.
Therefore, between any 2 points, we consider distance as points in manifold, distance in Euclidean.
Exactly. Yes. Yes.
But why it is better?
Here is the example. So here we have so why it is more accurate. So this picture shows why it's different, right? So we have the Euclidean distance between red and green smaller than between green and blue, but distance along the manifold vice versa. But why it's more accurate? Well, actually because this manifold, so for example, I take a neural network and process my photos, for example, and then I get points in some Euclidean space. They lie on the manifold, and structure of this manifold reflects the relationship, I'd say, between those points. Like why we take, I don't know, why we using linear regression, why we take point on this straight line as a prediction for our process. Well, because we see and suppose that those points lie near this line. So this line, this one-dimensional manifold, describes how I don't know, their nature, right? And in general case, this manifold, which exists by the manifold hypothesis, this manifold describes the nature of the data points. And that is why when we walk along this manifold, this is better estimation. For example, we can look at the curves along this manifold like continuous deformation of my photo. So for example, just random example, I have, I don't know, a golf player who is hitting a ball. Initial position is here, and the final position when the ball is, I don't know, far away is right here. This curve would give me a continuous set of photos, a continuous set of pictures where he is moving. It's continuously deforming. And if I take this route, then it would contain some, I don't know, Lovecraftian horrific creations with many hands, many balls, and I don't know what else. So those points are not meaningful in the sense of this data set, and those points are. That's why looking at the manifold is more accurate. All right, so I think, yeah, my last 2 slides. The question is, can we actually construct this manifold? The answer is partial yes. So this manifold hypothesis, unfortunately, hasn't yet been proved analytically, so I don't have, again, and no one has the theorem that, yes, under certain conditions, the points lie in a closed vicinity of a manifold. But experiments, the data from real world, time after time, affirm that yes, this manifold exists, though it may be quite bad. So, for example, it may be not connected, it may consist of several, or maybe many, a lot of distinct pieces, and in other ways it also could be pretty bad, but still it's a manifold or something very close. Then, how to construct it? We have some dimensionality reduction techniques which not only estimate the dimension but also help to create to construct the manifold. A good example is nonlinear principal component analysis, which finds not this linear subspace but something more curved, so some surface, some manifold. And also there are different attempts to approximate the manifold in the literature. It can be found, and if anyone is interested, I could just give the references, give the papers. So people try to intersect quadrics, so quadratic manifolds, consider something called cylindrical bundles. I wouldn't go into that right now. And using other geometric methods, looking at the data cloud to approximate the manifold. And the last slide of this talk, what should be done? What are the first directions? Where do we go from here? So, first of all, we should concentrate on making better matrix constructions. So, look at data cloud, try to construct a manifold, try to create some accurate Riemannian metric for it. Then we can also look for new methods of dimension estimation. Minkowski dimension is good and nice, and probabilistic methods are good, but again, as we discussed, they don't work always. And first of all, it would be very good, very profitable to, that's right, formulate some theorems which state exact conditions when this method works, or this method works, or none of the methods works. And we can devise new methods. The third point is, well, what I was talking about just right now, how to make better approximations of this manifold, more accurate, more, and easier computable. And finally, as I said, it would be great to have rigorous formulation and analytical proof of the manifold hypothesis to exactly understand what is the geometrical structure of the data points taken from the real life. So I think that that's all for my short talk today. So if there are any questions or comments or discussions, please, I'd be very happy to answer whatever I can. Yeah, sure.
Actually, from your last two slides,
Uh-huh.
I was kind of feeling that most of these questions are not solved, but there's a lot of work in this area.
That is true. So yes, my last slides shouldn't be taken as the sign that this field is completely, terra incognita. There are plenty of works on all those bullets. So people try to prove manifold hypothesis and understand exactly what it means. There are works on approximation of the manifolds, different methods of dimension estimation, some methods, not that many, but still some methods of construction metric. But still, there is a lot of area of improvement in this in this field. That's why I put them here. Yeah.
I was trying to mention the diffusion maps, vector diffusion maps.
Right. Yeah.
Pretty much answering some of these questions.
In some way, yes.
I don't know if you managed to compare your results with what they have now.
Not really. It's something in our plans, but not yet.
First picture, you are using two items to create closed Y. You can use one item. Y2.
One item. What do you mean?
You use two pieces of
The green, the blue and green ones. Yes.
Y2. You can use one. Can you?
No, because if I take the whole surface of the torus as one piece, it wouldn't be a deformed disk.
Can these?
Yes.
Okay.
So yeah, that's right. So here I used two disks to create half of the torus. Of course, I could No, no. So for the torus, the minimum number of disks would be 4. So I would have this one, and the same on the other side. Yeah.
But how we can obtain among two matrices? What is better?
Well, that's a good question, and I think that the most accurate answer is that if we use supervised learning, we have our training data set, and we have the labeled data, and then we can just adding to it, look at both metrics and decide which better reflects what is happening with the points. But of course, if we somehow constructed this manifold, then we can just look which of the metrics is actually the metric on the manifold and which is not. And then take the one on the manifold. If both of the metrics are on the manifold, then, well, only experimental. Because, of course, on the same manifold, we can define a lot of Riemannian metrics, and they're not better or worse per se. So they're more suitable or not, and that depends on the data.
And have you tried any persistence homology ideas on this?
I know of some works in this area. So in Moscow, our colleagues in Skolkovo used some of the techniques, but I don't know quite about the results. So yes, that's something I debated, including in this talk, and decided against it. But
The
yeah.
last line, if you go to the last line,
Mm-hmm. Yeah, that's correct. That's correct. Thank you very much. It's been a pleasure.